Our last lesson concerns molecular dynamics. To start off, let's return to a term that I introduced at the beginning of lesson 29, and that is gellium, which means that we assume the tip and sample are of uniform density, no atoms, no electrons, just uniform. Well, at the macro scale, that's a fine assumption, but perhaps at the scales we're working, maybe it isn't. So let's introduce atoms now. Voila, here's a sketch of a few atoms in a tip and a few atoms in a sample. And already you can probably appreciate that this kind of computation is going to get pretty complicated because for each atom we have here, we have to sum forces on it from the inner atomic potentials of the surrounding atoms and find the acceleration, and using the acceleration find the motion of the atoms. And of course they're all jiggling back and forth with temperature. So we are going to go through this and I'll tell you a little bit more about it, but first let's look at a molecular dynamics simulation that's as a function of temperature so you can see the jiggling. Here we are. This is a simulation of a silicon carbide alloy where the atoms of silicon are represented by the spheres of yellow, the atoms of carbon by the spheres of blue, and hydrogen in gray. It's going to start off at 4,000 degrees centigrade, and you'll see that the atoms move quite a bit. Then we cool the system to 1,000 degrees centigrade, and the atoms slow down. And then the final state is 300 centigrade, and you see that there's not much movement at all. So how does this work? In this particular simulation we have 500 silicon atoms, 500 carbon atoms, and some hydrogen atoms. For each one of those atoms, the computer is remembering its mass, its initial position, initial velocity, and each one of those atoms has an inner atomic potential with the other atoms in the neighborhood, similar to the Lennard-Jones potential that we've mentioned before. And as we've mentioned before, you can get the force acting between two atoms by taking the negative derivative of that inner atomic potential. And so for each atom, you sum all those forces from all of the inner atomic potentials from the other atoms, and that gives you the mass times the acceleration of the particular atom under consideration. You find that acceleration, and you use that to get the velocity of that atom just from regular kinematics that you studied in introductory physics. So in fact, these simulations are just Newton's laws applied again and again and again. The computer has to go through a lot of steps, so these calculations take some time. And of course, real situations have many, many more atoms than just 1,000. So 1,000 or maybe even 1,000,000 atoms is about all that computers can do at the moment. You also see that we're looking at a fairly small volume of material. And what we do to try and make that small volume more realistic is we impose something called periodic boundary conditions. And that means that despite there being boundaries here and here to what we see, when an atom pops out of this boundary here, it could pop into that boundary there, and likewise If an atom goes this way, it'll pop back in this way. And the same is true for the third dimension. So when we look at this video again, you'll see some flickering of atoms near the boundaries, even at 300 degrees centigrade. How do we know what the temperature is? How do we control the temperature? Well, we use the equipartition theorem, which is 3/2 Boltzmann's constant times temperature in Kelvin is equal to 1/2 m mean square velocity. Okay, so the right-hand side is just the kinetic energy, left-hand side, thermal energy. You might notice that this is a little bit different than what I've told you before. There's a factor of 3 here instead of a factor of 1. Before, we were looking at the vibrations of a cantilever, which are pretty much constrained to move only in one direction. The 3 here is because we have 3 directions, and what that means is the velocity on the right-hand side, that's velocity in 3 dimensions instead of just the up and down motion of the cantilever. In any case, it's through this relationship that we can control the temperature. We use the mean square velocity and the mass of the atom to either know what the temperature is, or if we want a specific temperature, to constrain the mean square velocity. I'll play the video again, and this time, in addition to watching the amount of jiggling as a function of temperature, I'd like you to observe the periodic boundary conditions where atoms move in and out of the edges, including the edge that's facing us, meaning if they disappear from our view, they would reappear at the back of this cube of atoms. Here we go. Lots of motion at 4000 C. Less motion at 1000 C. And now at 300 C, our eye is attracted only by the flickering because of the periodic boundary conditions in 3 dimensions. These lessons concern atomic force microscopy, where we have a tip in a sample. That doesn't pose any problem for molecular dynamics researchers. You can set up your atoms in any position you wish. And for the case of AFM, where we have a tip in a sample, the difference between what we just saw and an AFM setup is that you have what are called fixed atoms away from the interface and free atoms at the interface between the tip and the sample. Now the difference between fixed and free is the following. The fixed atoms still jiggle back and forth with temperature, but their mean position is constrained. Whereas the free atoms, they'll jiggle back and forth too, but they may change their positions. Now this can simulate transfer of material or damage to the tip or the sample. Fixed atoms, they can be regulated. Their mean speeds can be constrained, and this can give you a constant temperature. So it's as if the atoms that we have in our simulation, which number just thousands, maybe a million, are connected to a reservoir, meaning that effectively, as far as temperature is concerned, we've connected these atoms to a macro scale object. And the advantage of having fixed atoms is that you can move the tip with respect to the sample either laterally to investigate friction or perpendicularly up and down to simulate force curves. And a lot has been learned via molecular dynamics simulations about tip-sample interactions. When you first see molecular dynamics simulations, you're impressed with them. They're really fun to watch. But it turns out that when molecular dynamicists get together, most of their effort, most of their discussion is in the potentials. It turns out that the potential that we've been discussing, the Leonard-Jones potential, that's one of the simpler ones, and it applies only really well to noble gases at very low temperatures. The major thing that it's missing is the directionality of bonds that most atoms have. So you have to be very careful about how your potentials do or do not reflect reality. Here are example images from a molecular dynamics simulation of a nickel tip pressing into a gold surface. The gold surface, the atoms are color-coded so you can see which layer they originate. And two of the interesting predictions was that as you bring the nickel tip towards the gold surface, there's an instability where the gold atoms are attracted to the high-energy surface of the nickel. So it's completely analogous to the cantilever instability, but now instead of a macro-sized object, the cantilever beam, we're talking about the first layers of gold. That's the image on the left. In particular, look at this interface where these gold atoms have moved forward out of the surface. After we push the nickel tip in and then withdraw, there's this formation of the atomic wire on the right, and there's some very interesting electrical conduction effects through those atomic wires, as seen experimentally. So this was a very fun project to be involved with. Congratulations for reaching the end of 30 lessons on atomic force microscopy, the first 18 of which were on the fundamentals, and the last 12 on interpretation of force curves, where we went through force curve acquisition and some problems, surface forces and contact mechanics, and touched upon various ways of modeling force curves. I did my best, but I would like to give you a little caveat emptor right now. I believe I missed some minus signs. I believe I might be off by factors of 2 here and there. But I believe also that the errors on my part have been small, and that these lessons should provide you a good basis of discussion and a good basis on which you can build your knowledge of atomic force microscopy, scanning probe microscopy. There's a lot more to learn, and I wish you well.